Okay, we are back for 8.4, which is going to deal more with logarithms, specifically properties of logarithms that are going to lend itself useful to solve equations as we move forward. Okay, so there is a handful of logarithms here, but first we have two learning targets. The first is that you can use properties of logarithms to evaluate, and that you can use the properties of logarithms to expand or condense logarithmic expressions. So there's going to be times where we're going to start with something nice and neat, and we're going to expand it out so we can solve, and then the other way around where it's expanded out and we're going to condense it down into something nice and neat. Okay, let's go ahead and look at these logarithms. Okay, so when I look at these logarithm properties here, so the first is the product property. So if I have a logarithm with a base, and I have two parts that are being multiplied together on the inside, you can actually separate those out with the same base. So if I have log base b of m times n, that is going to be the same as log base b of m plus log base b of n. Okay? Quotient property is very, very similar, but instead of addition, it's subtraction. So if I have log base b of m, and I take away log base b of n, that's going to be this as division here. Okay, and it's important to note that it isn't just going from left to right here. If I have this, I can backtrack into this as well. Okay, so this is like the important stuff when it comes to these properties, is understanding that it's not a one-way street; it's a two-way street. Okay, the last is the power property here. So if I have log base b of m to the n power here, okay, what I can do is I actually can pull that power out in front and leave everything alone. Okay, so here I have the change of base formula here. Okay, so if I have log base c of a is equal to log base b of a divided by log base b of c. Okay, so I can take like a third number here and keep that base here, okay, and just take your logarithm with that base of a and c. Okay, and that will change the base automatically. Okay, that works with here. If we look here, it's almost the exact same thing, but instead of it just says log, which indicates log base 10. Okay, and here's the same thing, but instead of ln, okay, we know that that's log base e, which is, the exponential natural growing rate. Okay. So let's actually try to use some of these properties. Okay, so this one says I'm going to use the fact that log base 2 of 3 is about approximately 1.585, and log base 2 of 7 is 2.807, and we're going to evaluate these logarithms. Okay, so what am I looking at here? I have log base 2 of 3/7. Okay. Now, it's not a coincidence that I have a 3 and a 7 here, but let's look at this. I have the division here, so let's look at this quotient property. What I can do is I can actually split this up into a logarithm that involves two things without division here. So I actually can say that this is the same as my log base 2 of 3. Right? This is the first part, m and m, minus log base 2 of 7. Okay, so log base 3, or log base 2 of 3 minus log base 2 of 7. Okay, well, I know what log base 2 of 3 is. It's approximately 1.585. And I know log base 2 of 7 is 2.807. And now all I have to do is subtract those numbers. Okay, 1.585, and I'm going to take away 2.807. And I'm going to get negative 1.222. And this is an approximation. But what does this mean? This means if I raise 2 to the negative 1.222 power, it's going to give me roughly 3/7. So let's actually see that happen. So we know that 3/7 is about 0.429. Okay, so if I take 2 to the negative 1.222, and again, since I've rounded here a couple times, it's going to be a little bit off, but you can see that it's very, very close approximation of that. Okay, so So this is telling me that if I raise 2 to the negative 1.222 power, I'm going to get 3/7. Okay, so let's look at this next one. This next one is log base 2 of 21, and I need to figure out what that's equal to. Okay, so let's look at this. Well, I know 21 is the same as 3 times 7. So I can actually rewrite this as log base 2 of 3 times 7. Okay, because then now what I have is I have a product, okay, and there's a product property, okay? I can split up the two numbers I'm multiplying into two parts and add them together with my logarithm, okay? So now what I have is I have a log base 2 of 3 plus log base 2 of 7, okay? Log base 2 of 3 is 1.585. Log base 2 of 7 is 2.807. And now I just have to add those numbers together. 1.585 plus 2.807. And I typed something in wrong. I have an extra decimal. 4.392. Okay. So that means if I raise 2 to the 4.392 power, I'm going to get 21 approximately. Okay, and again, when there's some rounding error in here, so there's naturally not going to be perfect, but if I put this in, you can see it's going to be pretty darn close. Okay, 20.995. Okay. Next one here is I have for log base 2 of 49. So we need to think about the numbers that I've given here and 49. So I know I have log base 7, and specifically that I know that 7 squared is the same as 49. So I'm rewriting 49 as 7 squared. And so now I can use the power property. Okay, power property tells me I could take that exponent of that inner part of the logarithm and I could just pull it out in the front and multiply. So 2 times log base 2 of 7. All right. Okay, so now 2 times log base 2 of 7 is about 2.08 or 807, 2.807. And then I just have to take 2 times 2.807 to get 5.614. Okay, and then again, some error in here because of rounding, but we're going to be able to see that if I take 2 to the 5.64614 power, I'm going to get approximately 49. So 2 to the 5.614 power, and that's 48.975, so that would round to 49. And so that looks like we're pretty good. Okay, so here is just how we can apply some properties in a simplistic way to get some numbers that we need. Okay, and so then let's go ahead and pause the video and try A through C on the right-hand side. Okay, at this point, I've already assumed that you've paused the video. You've already tried these on your own, and now you're just checking your work. Okay, so I know that this is the quotient one, so I'm going to take log base 6 of 5, and I'm going to take away log base 6 of 8. Okay, log base 6 of 5 is 0.898 approximately, and log base 6 of 8 is 1.161. So now all I need to do is subtract those two numbers. Minus 1.161. And it's negative 0.263. And again, if I wanted to, I could take my calculator, take 6 to the negative 2.63 power, and I'm going to get approximately 5/8. Okay, this one here, log base 6 of 40. I know that this is the same as log base 6 of 5 times 8. I know 5 times 8 is 40. Okay, and so now I have a product, and my product says I can split it up using addition. So that's exactly what I'm going to do. So I'm going to say that this is the same as log base 6 of 5 plus log base 6 of 8. I know log base 6 of 5 is 0.898. And log base 6 of 8 is 1.161. And all I have to do is add those together. 0.898 plus 1.161, 2.059. Alrighty. Last one. Okay, so C. This one is a little bit different, but as I look at this, I want to think about 125 and what number. Well, it's definitely not 8. 8, you know, if I take 8 to any power, 125 isn't going to be nice and neat, but I can take 5 to a power and get 125. In fact, I can get 5 to the third power, and that's going to be 125. Okay, and so now I just have this power property, just which tells me pull that exponent out to the front. Okay, so now I have 3 times the log base 6 of 5. Okay, so this is going to be 3 times log base 6 of 5 is 0.898. And 0.898 times 3 is 2.694. Okay, and again, I can take 6 to this power, and I'm going to get roughly 125. So here I take 6 to the 2.694 power, and you know it's approximately 125. Again, some error here because these are approximated numbers. Alrighty, let's keep moving. Okay, so now this next one is what we're going to do is we're going to rewrite a logarithmic expression, which is going to probably require us to expand it out using the same properties that we did before. Okay, so I have ln here, which tells me that my logarithm base is going to be e, because ln indicates to me natural log. Okay, so here, right off the bat, I have the division. I'm dividing 5x to the 7th power divided by y. Let's go ahead and split that up. So this is going to be the natural log of 5x to the 7th minus the natural log of y. Okay? This is just using the division property. Okay, then the next one is I actually have multiplication, right? I'm multiplying 5 times x to the 7th. So this can be split up once again into the natural log of 5 plus the natural log of x to the 7th minus the natural log of y. Okay. And then there's one more part, as there always is that I'm taking this to the 7th power. And so what I can do is I can pull that value out, or I can pull that exponent out and multiply it by the natural log of x. So here I have the natural log of 5 plus 7 times the natural log of x minus the natural log of y. Okay, and this could be written in basically any order as long as this negative sign stays here. So you didn't have to do division, then multiplication, then exponent. You could have done it in a couple different ways, but to me this is probably the best route. Okay, so this is us expanding a representation here. Okay, so now as I look at D, the natural log of, as always, pause the video, try letter D on your own, and then check it with what I'm about to do right now. Okay, so I'm dividing. So the division property tells me that I can split it up, but I'm going to use subtraction when I split it up in top minus bottom. So here, the natural log of 5 divided by 12x is going to be the same as the natural log of 5 minus the natural log of 12x. Okay, so I'm going to look at the natural log of 5 and ask myself whether that can be simplified or not, which it cannot. Okay, and then I'm going to look at the natural log of 12x. So 12x, we should know, but at this point, this means 12 times x. Okay, so this is multiplication. So now I can say that this is the natural log of 12 plus the natural log of x. Okay, natural log of 12 and the natural log of x. Okay, and I probably need to put parentheses around this because I'm simplifying this entire part here into this. Okay, because I'm subtracting this whole thing, and this whole thing is equal to this. Okay, and so the last, I can just distribute my negative here to get the natural log of 5 minus the natural log of 12 minus the natural log of x. Okay, look at each part. And it cannot be expanded out anymore. Each part individually is as simplified as it can be, so that is just going to be it. Okay, let's actually condense. Now, basically what we're doing is we're doing the opposite of 4 and D and 5 and E. We're going to start expanding, and we're going to work backwards. All right. So one thing that jumps way out to me is that 3 log of 2. Okay, first off, when it says just log, we need to think about what base that is. May not be necessarily super important for this problem, but for other problems, log with no base written is indicated to be log base. Yes, 10. Okay, so as we look at this, we have log base 10 of 9 plus 3 times log base 10 of 2 minus log base 10 of 3. So I'm looking at this here, and specifically when I have that multiplication out front, that really indicates to me that we had an exponent, just like we did here. Okay, just like we did here. So I'm going to rewrite this as log base 10 of 9 plus log base 10 of 2 to the third power minus log base 10 of 3. Okay. So when I look at this here I'm adding, right? I'm adding these two parts together. So when I added, that means at some point those have been multiplied together. Okay. So we can condense this down together into log base 9 times 2/3 minus log of 3. Log base 10 of 3. Okay. Adding tells me I had multiplied. Okay. And the subtraction tells me that we have divided. So here I have now log base 10 of 9 times 2 to the third power over 3. Okay. And then here we just have to do a little bit of simplification. Okay. 2 to the third power here is 8 times 9 is 72 divided by 3 is 24. So this whole thing is equal to log base 10 of 24. Okay. So what you just want to do is you want to find the parts that you can, that you know have occurred at some point. You're just identifying properties that were in the table on the first page, and really we're just working backwards from 4 and D. Okay, so here I'm looking at ln, which is the natural log, which is log base e. Okay, so as I want to do this exponent here first, all right? At some point, 3 times the natural log of 3. So here I have the natural log of 4 plus the natural log of 3 to the third power minus the natural log of 12. Okay, so that gets rid of this multiplication of 3, tells me that that was an exponent. And here now I have addition, which tells me these have been multiplied. So 4 times 3 to the third power minus the natural log of 12. Okay, and so then subtraction tells me that we divided. So this is the natural log of 4 times 3 to the third power over 12, which is, well, 3 to the third power is 27. So let's go ahead and go 3 to the third power times 4, and then divide by 12. This is the natural log of 9. Okay, so basically what these problems do is they just go back and forth from each other, getting just applying the properties in different forms just to simplify it down. This one's the opposite of that, getting something complex and expanding it out. This one, getting something expanded out and condensing it down, using those same multiplication, subtraction, or multiplication, division, and exponent properties. Okay. Let's actually use those change of base formulas that we talked about at the top, or at the front of the page, because they're very helpful because, at least in my opinion, I'm going to show you the calculator for a moment here. In my opinion, when I'm looking at the calculator, we have log and ln. So when I hit log, it just comes up with log. Okay, and so what that is doing is that is automatically going log base 10. Not log base 2, 3, 4, 5, any other number. It's going to be log base 10. Okay, same with ln. ln is just automatically natural log. Okay, so if I go natural log of e, and then that should just, give me 1. It's just the natural log. It uses base e. So there's not really a nice way to have logarithms in your calculator that aren't base 10 and that are not base e. So a lot of the work is going to have to be done through base 10 or through base e. Okay? And so what we need to do is we need to identify the change of base formula, which I'm going to rewrite here on this page because we're going to use it for the next 4 examples. Here, I think I got it over here. Okay, so we know that just kind of off to the side that if I have a log base c of a, that we can rewrite that as log base 10 of a, or over log base 10 of c, or really the base doesn't matter. It could be e, 10, 5, 8, doesn't matter. But for us, log base 10 and log base e are going to be the best to use because that's what's going to be on our calculator. Okay, so let's go ahead and use the change of base formula. Okay, so here I have log base 3 of 8. And I want to figure out what that's equal to. I want to know what number do I need to raise 3 to get 8. Now we know it's going to be a little less than 2 because 3 to the second power is 9. But I want a little bit more precise than just a little less than 2. So we can use our change of base formula, and it's going to be basically just looking at this here that we have written off in red, is that I can use base 10 and of my a value. So my a value here is 8. So this is going to be like log base 10, not base 10, log base 10 of 8 over log base 10 of 3. Okay, so basically what I can do is I can just take my calculator now at this point. Okay, and again, the log, we're doing log base 10 here. So we're going to use regular log button. Okay, so log base 10 of 8 divided by log base 10 of 3. Okay, and then what that's going to do is that's going to give me log base 3 of 8. Okay, and so that's going to be 1.892. And let's round to the third number. So 8927. 7 is going to round that 2 up to a 3. So let's say 1.893 approximately is going to be my number. Okay, now here's the nice thing is I can just take 3 to the, and then what I can do is I can hit the second button, and then this negative, it says ANS for answer, my previous answer. Okay, so then what I'm doing is I'm not rounding at all. I'm using the exact answer here, and then it's going to give me 3 to that previous answer is 8. which is perfect because that's exactly what we were looking for. We were looking for what number raised to the power, or what number do I need to raise 3 to get 8, and this here is, this is the exact and this is the approximation. Okay, so what I want you to do is, well, also common logarithms might be helpful to know that that is base 10. Okay, so let's go ahead and do F. Actually, you all do F, and then check it with my work right now. Okay, so we're going to use the base 10 change of base formula. So this is going to be log base 14 over log base 8. Okay, so here I can go ahead and use my calculator to go log base 10 of 14 divided by log base 10 of 8. It's going to be approximately 1.269. This 1 would not round that 9 up. It would keep it the same. Okay, and then again, I should be able to take 8 to this power, and it's going to give me 14, which is exactly what we wanted. Okay. All right. Almost there, folks. The next little section is absolutely awesome because it's basically the exact same thing, because the only difference is we're going to use the change of base formula using the natural logarithm, which is base e. Okay, it's base e, and then that formula is if I have log base c of a, I can change that to ln, natural log of a, divided by natural log of c, and that's just going to give me my answer. It's basically the same thing. They actually can be used interchangeably. You can use them however you wish. If you like base 10 better, use base 10. If you like base e better, use base e. Okay, so let's go ahead and do this. Okay, so I have log base 6 of 24. So I want to know what power do I need to raise 6 to get to the 24th power. And so this is going to be pretty much, we just have to take the natural log of 24 and divide it by the natural log of 6. Okay, so let's go ahead, and ln here is your natural log. So natural log of 24, and we're going to divide it by natural log of 6 to get 1.7737. So this 7 here is going to round that 3 up to 4, so 1.774. And again, I can raise 6 to this power and find out that that is going to give me 24 on the dot, which is exactly what we wanted. Okay, pause the video. Try G on your own. Okay, so I'm taking the log base 26 of 9, so I'm trying to figure out what power do I need to raise 26 to get 9 on the dot. So let's use our change of base formula using natural logs. So I'm going to take the natural log of 9, I'm going to divide by the natural log of 26. Oh, so this is 0.6743. That 3 is going to leave that 4 alone. So 0.674. And again, I should be able to take 26 to this power, and it's going to give me 9. Okay. Okay, lastly, a lot of times with all this stuff that we do, you know, a lot of times it's really hard to have context to some of the stuff, but oftentimes what these do is technology uses logarithms, exponential functions, any type of polynomial, really anything that we've done in this class at any point. It's really all it does is some sort of technology is going to use these functions as a model to predict things or to estimate things or to give us you know, some numeric idea of what's going on. Okay, and so that's what this application problem is going to be. So for a sound with intensity I in watts per square meter, the loudness, L of I, so this is my function, of this sound in decibels is given by the function 10 times log base 10 of I over I naught, where I naught is the intensity of the sound of a barely audible soundtrack. Okay, and an artist in a recording studio turns up the volume of a track so that the intensity of the sound doubles. How many decibels is the loudness increases? Okay, so we're going to let I be the original intensity. Okay, so we're going to let I be the original intensity. Okay, so that means that for this particular problem, we know that this is going to be, if I take the loudness of 2I and I take away the loudness of the I, this is going to be how much it increased. Let's think about why. Okay, so this here is the original. Okay, this is the original, like let's say they had, a dial that went up to 100 and it was at 25 or whatever. That's the original. And then doubling would be 2I. Okay, so if I want to find, if I would like to find the original, I would just plug in I into this formula and go. And here I would do 2I because this 2I is going to represent the double. Okay. So that means we can just use this formula kind of twice. So I can say that this first part is going to be 10 times log base 10 of 2I over I naught minus 10 of log base 10 of I over I naught. Okay. So as I look at this here, I'm looking and I actually see that they each have a factor of 10. So like it's important to note that like this little part that I have underlined here and this little part I have underlined here, I understand there's a lot of letters, a lot of variables. That actually there's more letters than there are numbers here, but they do just represent numbers. It's just there's a lot of unknown parts, so we don't really know all the parts that we have. But one thing that they do have in common is they each are being multiplied by 10. So just like in any of the previous factoring problems that we've ever done, we can actually just pull a 10 out. So let's go ahead and pull a 10 out here and just say that the log base 10 of 2I over I naught minus log base 10 over I naught. Okay, and we actually do know that I naught is 10 to the negative 12th, but we're going to see here pretty soon that that actually isn't going to matter a whole lot. Okay, so after I've done that here, if I look here, I have 2 times I. Okay, that's the multiplication property. Just simply the multiplication property. So what I can do is I can rewrite this as log base 2 plus log base 10 of 2 plus log base 10 of I over I naught minus log base 10 of I over I naught. Okay, so let's look at this here. Multiplication, I would do the 2 times I over I naught, right? And using the multiplication property or the product property, I could just split it up using addition. Okay, and something really, really important happens here. Okay, what happens is I have positive log base 10 I over I naught minus log base 10 of I over I naught. These numbers here are opposites of each other, and when opposites where I have the same thing being subtracted, these just cancel each other out. They're just gone. So what's left over? Okay, so this is now just left over with 10 times log base 10 of 2. Okay, and so that's like the exact answer, but it wants to know how many decibels did this whole thing increase by. And really all we can do is we could take our calculator, just go 10 times log of 2, log base 10 of 2, and it's about, so it's about 3.010 decibels. Okay, about 3 decibels is by how much this particular volume increased in the recording studio. Okay, and again, it just uses to model a whole bunch of different information. Okay. Otherwise, as I look back through our learning targets, here, knowing how to use the product quotient and power property pretty extensively. Okay, we use this a lot in this section, and although this is super important, I have to say the change of base formula is extremely important, because if you ever want to be able to use a calculator to evaluate any of these, a lot of times you're going to have to end up using this change of base formula, particularly with base 10 and base E. So this is base 10 and this is base E. Okay. Otherwise, now's a good time to stop and move on to the 8.4 homework. And otherwise, I will see you at the beginning of the next lesson.